Welcome to this lecture for Grand Challenges in Engineering Systems. This is the first of 3 lectures on Engineering Economics Fundamentals. The agenda for this lecture is to cover the basics of discounting, and then there will be a second lecture on benefit cost analysis decision criteria, how we decide whether to pursue or not pursue a particular project, and then a third lecture on the economic view of costs, which is quite different from the accounting view of costs. So the basics, what is discounting? Discounting is understanding the time value of money, and this is crucial to making decisions about investing in large, long-term projects such as engineering challenges. So here's how I usually start students thinking about discounting. Suppose that I were to write you a promissory note saying that I would pay you $1 a year from now. How much would you be willing to pay for that promissory note? And the first question, of course, is would you pay more than $1 or less than $1 for this promise by me to pay you $1 1 year from now? Most students say that they would pay less than $1, that this note would be worth less to them than an actual dollar. So if they could get it for maybe 90 cents, maybe it'd be worth spending 90 cents now to have me pay you $1 later, but they wouldn't pay a full dollar. And when asked why, the first reason that they usually give is inflation. So what is inflation? Inflation means that prices go up over time. So in other words, $1 will buy less in a year than you can buy with $1 now. So I should pay less than $1 now for $1 that I will receive a year from now, because that $1 that I'll get a year from now, I'll be able to buy a smaller basket of goods and services than I could buy if I go out now with $1. So this is certainly a good reason to pay less than $1 for that promissory note. However, from the standpoint of a policy analyst, if inflation is a general rise in all prices, why bother with it? If the ratio of prices stays the same and it's really just the devaluation of the currency, why worry about it? Yes, prices will be higher tomorrow, but wages will also be higher tomorrow. Inflation tends to be very volatile. It shifts around. Sometimes it has runs of being very high. Other times it has runs of being very low, depending on macroeconomic conditions, and these are very hard to predict. So why don't we just take this confusing and hard to predict factor out of our analysis and pretend that no inflation will occur, and so we work in constant or real dollars. And sometimes that terminology is a little bit confusing. What it really means is let's do everything typically in present dollars. So we say let's just denominate everything in 2014 dollars and pretend as we go into the future that prices will still be denominated in 2014 dollars. There will be zero general inflation throughout the economy. So the other way to do it is to try to estimate inflation and actual prices going forwards, and this is called working in nominal dollars, because it's the nominal dollars that would be received in the future. You could also call it future dollars, probably a clearer term. So it turns out that you can do either. You just have to be consistent. So the actual financial markets work in nominal dollars. There is no such thing as a 2014 dollar in the market. They're just dollars, nominal dollars at different points in time. So when you're using nominal dollars, you would use market interest rates. If you want to think about the cost of borrowing and you're doing a nominal dollar analysis, then your interest rate is the market interest rate. Because those market interest rates include market expectations of inflation. Now it's often simpler, though, just to not worry about inflation, not worry about trying to predict it. And in that case, we work again in constant or real dollars. And so in this case, you have to use estimates of real returns. So this can be a little bit confusing because these are not numbers that you can go and look up in the financial markets. They're the after inflation returns, the returns in real purchasing power. And these, of course, are lower than market interest rates because they don't include inflation. Now, for a first approximation, when both inflation and interest rates are low, say when they're both below 10%, you can just add the real return to inflation to get the market interest rate. There are some subtleties about that in terms of that's actually off by a factor of the inflation rate times the real return. I'm not terribly concerned in going through that algebra in an introductory lecture. So just know that it's a reasonable approximation to view the market interest rate as being the sum of the inflation expectation and the real return. And that to a first approximation, that view of the market interest rate is accurate. In terms of what values should we actually use for a real interest rate, something around 3 to 5% is probably a reasonable range. One thing that we haven't talked about, because usually students are too polite, is we haven't talked about risk. So if you have a very risky investment, it is going to have to return more on average in order to induce people to pursue that investment. So a risky investment might on average return 5% towards the upper end of that real return range. A very safe, secure investment will tend to return towards the low end of that range, maybe around 3% in real terms. And the reason I said that students are too polite is if we go back to the original question of, how much would you pay for this promissory note, one reason that you might pay less than $1 besides inflation is that you might not trust me to repay you. Again, students are usually too polite to mention that, but certainly if I'm a very risky, untrustworthy person, you would pay less for this. And so in that sense, I would have to pay a higher interest rate, a higher effective interest rate if you don't trust me. If I'm considered risk-free, I'm going to pay, then you would still pay less than $1, but that difference might be very small. Maybe you'd pay 99 cents, and so I'd have an effective interest payment of only 1 cent because I'm considered trustworthy. Okay, let's take currency out of this altogether so that we can kind of forget about inflation. And let's say that you have a goat, and for purposes of this question, consider it a female goat in the prime of its life, and I say, can I borrow that goat for a year? And I'll give it back to you next year, and it's a long-lived goat, so it won't really have depreciated very much. Is that good? You get a goat in the future, you give up a goat now. And the natural reaction, I think, is, well, no, if I can keep my goat for a year, the goat produces goods for me. The goat may give birth. Again, I said it was a female, so it may give birth to young, and may have more goats. So that's productivity. That's growth of capital, innate growth of capital over time. Similarly, it may be giving me milk throughout the year, and that's valuable to me. So it's, in a sense, paying dividends in the sense of giving me milk on an ongoing basis. So when I borrow your goat for a year, I'm depriving you of the wealth that it generates over time. And so I should have to pay you for the privilege of having the goat, for the privilege of having the capital, the goat, and putting it to work creating wealth for me. I should have to pay you for that privilege. So that's another factor that leads to interest rates. Again, if I'm going to borrow a goat from you, I better repay you not just one goat, but some share of all of the milk and offspring that goat has given to me over the year. So interest is one way of doing that, in which you repay back more than you borrow. And the reasons for this, again, to compensate for inflation. In many cases, in this class in particular, I'm going to recommend that you work in constant dollars and ignore inflation. It becomes just another distraction that complicates your analysis. The other reason for interest is to compensate for the loss of productive capital. Wealth can be put to use to create more wealth, and when you lose access to that productive capital, you lose access to the benefits that it could have given you over the time between when the borrower borrowed it and when the borrower gives it back to you. So the borrower has to give you some additional return to incentivize you to part with your capital for a period of time. The other is compensating for the risk of default. If you think that this project might not happen, that I might not repay you your dollar, that I might accidentally kill your goat and not give it to you over time, then in those cases when I am able to pay, you're going to require a greater incentive, a greater interest rate. The last one is a little bit perhaps unclear, but pure time preference. Do we just like things now? You know, do we want to have it now rather than later? I think we do. There's some evidence for that, but it's not so clear that we should feel that way innately. Let's consider once more this question, though. You know, would you ever pay more than $1 for this note? And normally, I think the answer would be no. But suppose you were really afraid of losing your dollar. You thought that people were going to ransack your house and burn it to the ground. In that case, you might say, you know what, promise to pay me $1 in a year, and if you can keep it safe, I would actually be willing to pay more than that, because I've got plenty of dollars now, but I'm worried about these unstable conditions. I'm worried about loss of productive capital, and in this case, I am so worried about losing my wealth that to have even a guarantee of a small amount of wealth in the future would be worth, in essence, losing a part of my productive capital. If I'm going to lose less than I think I will in sort of the general unstable conditions of people coming and burning down my house, then maybe I'll be willing to take actually a negative interest rate. So negative interest is very unusual. It's not theoretically impossible. It would come about during a time of great upheaval and concern over loss of productive capacity. So this gets to the question particularly relevant for this class of how does technological innovation influence interest rates? And I would say if I live in a highly innovative society with advancing technology, that society, because this technology is very good at creating wealth from wealth. And so in that case, I need a greater incentive to part with my wealth for a time. So that productivity translates into a higher effective interest rate. All right, discounting is the development of quantitative formula for balancing the preference for money now versus money later. This assumes basically that there are financial markets such that I can borrow and lend to cover my needs. It doesn't address the issue of, oh, I really need the rent by the end of the month. It works on a concept called equivalence, which basically says as long as I'm getting interest and at the going rate I, then $1 now and $1 in the future, which earns interest at interest rate I, are equivalent to me. So how does this work mathematically? Let's introduce the concept of future value. In this slide, you can see I'm putting the term future value 1. So this is future value 1 year from now. So this is your dollar 1 year from now. Present value is the current value. So the present value, the future value of that note, that promissory note was $1, and I ask you what present value is, how much you would pay for it today. And whatever present value you said, if it's 90 cents or 97 cents, we would simply plug that in and solve for I, and we would know the effective interest rate. So the way interest works is you have a certain present value now. The borrower has to pay back more than the present value a year from now, or whatever the compounding time period is. After that compounding time period, the borrower owes 1 plus I times the present value. Okay, can we extend this to 2 years? Well, again, the way compounding works is that the interest from the first year is added in to the second year. So now we have, when we go from the end of year 1, it's like you borrow again not only the principal amount, the present value, but also the interest that accrued, so that the future value that you owe is the future value that you owed after 1 year times, again, this factor 1 plus I. So what we can do is we can substitute in for future value the formula that we had previously, which is basically the definition of interest, present value times 1 plus I. So we substitute that in, we get future value equals present value times 1 plus I times 1 plus I, or future value in year 2 equals the present value times 1 plus I squared. And I'm just going to sort of say by analogy we can generalize this to n years. The future value in year n under terms of compounding interest is present value times 1 plus I raised to the n. Now we can also solve for the present value of a cash flow in year n, and in that case we would simply divide by this factor 1 plus I to the n. And that factor, 1 over 1 plus I to the n, is called the discount factor. And let's think about this. I is usually positive, so 1 plus I is usually greater than 1. So 1 plus I to the n, where n is going to be compounding period, so again n is going to be a positive, generally positive integer. So we're raising a number greater than 1 to a positive integer, and it's going to get larger. So we take 1 over that, and we get a number less than 1. So we have 1 plus a positive number raised to a positive number is greater than 1. 1 over that is less than 1. So this discount factor is less than 1. And I'm essentially dividing or multiplying my future value by a discount factor, a number less than 1, to get the present value. So this is where the term comes from. I'm taking these future cash flows and discounting them, making them smaller to put them in present value terms. Does this mean that I care less about the future than the present? Philosophically, I'm going to say not necessarily, at least. Expenses in the future are less burdensome. Why is that? I can put a smaller amount away today to save for them. So $1 in the future is less burdensome than $1 today, again, because I can put less than $1 away today, and I will have my dollar in the future to meet that expense. Gains in the future, similarly, they're less helpful, since I have less time to invest them at positive interest rates and generate future gains. So there's a difference between discounting and innate time preference. It might be that I prefer a good now rather than later, but that's not necessary. It's not a necessary assumption just because you're doing discounting. If real returns are greater than 0, then I can invest $1 now and in a year spend the $1 on a good and have I, whatever your interest rate I, left over, versus if it's, it's $1, if I spend it now, then I've got nothing left over to invest. So discounting does not necessarily imply that you have a pure time preference. You can get this sort of valuing $1 or valuing capital more now than in the future just by virtue of having productivity growth, by having positive interest rates. So it can be any reason that you have positive interest rates can lead you to discounting, and those reasons for positive interest rates can include productivity growth as well as pure innate preference for a good now rather than later. In general, I try to discourage people from valuing goods now from later. It tends to be just kind of a psychological effect. We maybe don't value our future selves as much as our present selves, but our future selves will value their future selves as much as our present selves value our present selves. So I don't know that there's any particular justification for an innate time preference, but to the extent that we really can earn real returns over time, then there are valid reasons to apply these discounting formulas. All right, so I've shown you the simplest of the formula just for taking a lump sum now and turning it in, finding the equivalent lump sum in the future. One thing we're often concerned about are annuities. So here we have a lump sum, and we want to balance a stream of equal payments at equal time intervals. The most common annuity is where you borrow money, and then you make periodic payments over time to the lender. And those are typically spaced equally every year, more likely every month, and they are the same amount. They don't increase or decrease over time. So how would we represent the present value of that stream of payments where we're making a payment of size A for annuity every year? Well, the present value would be the first payment, which is due one time period from now, typically 1 month or 1 year, whatever time period you want. We apply our discounting formula, where we take the future value and divide it by 1 plus I, and then we go out 2 time steps and we apply the future value 2 formula that I just showed you right here. We would apply this formula. We would apply this formula for future value 2, where you would divide it by 1 plus I squared in order to get the present value. And so that's what I'm doing here with this term. And then similarly, the payment that comes in the third year would be A over 1 plus I to the third. And finally, the last payment would be A over 1 plus I to the n. And if we have the terms set up so that all of these annuities balance out our present value of the loan, then in some sense, by this doctrine of equivalence, that I have equal preference between money now and money later, as long as the money later is inflated by this, increased by this factor 1 plus I, then the lender is made whole, is compensated for the loss of his capital over that time period. So again, the typical case in which we would apply this would be a loan where you get a lump sum from the lender and it's repaid over time. There's something called a sinking fund, where you make a series of payments over time in order to meet a lump sum future expense. So I'll show you an example later on, and in that case, to find the value of the sinking fund, note that this formula would actually give us present value, so we then have to take that present value and convert it to future value. That may be clearer when we work the example later. All right, so how do we actually go about finding out that series? Do we want to sum up all n terms? No, that would be annoying. It's a geometric series. We can apply the geometric series formula and get this formula for present value, which, notice, does not involve a summation of n terms. We just have to plug in the size of the annuity, the interest rate, and the number of payment periods to get the present value. More often we use Excel, and in Excel there's the payment function, and you would type in first the interest rate, then the number of periods, and then the present value. Now, if you have a series with future value, you can actually add in another term there, and you can add in the future value. You have to be careful about sign conventions in Excel. The way Excel works it is that basically the annuity has the opposite sign of whatever you put in for present value and future value. So if you put in a positive present value, it will return a negative value of the annuity. Okay, if you want to find the present value of annuity, you use the formula PV, and again you would plug in the interest rate, the number of payment periods, and then you would put in A, which is the size of the periodic payment, and it will return the present value. And here again, if you want to, you can include a future value if there's some future value to this series. And again, you have to watch those sign conventions. The present value that it returns will have the opposite sign of the numbers that you put in for the annuity and future value. Okay, so here's the example I've been promising. We have a nuclear reactor, and we need to close this reactor safely in 30 years, and we need $2 billion to do that shutdown and safe storage of the nuclear waste at this reactor. So the question is, how much money do we need to put aside each year? And we're going to assume 3% interest rate. So this would be probably for a case where we are doing a constant dollar analysis, and we would therefore have a low interest rate because we are not using a market interest rate. We're going to just look at real returns that we might get. So we have current ratepayers put aside a certain amount every year, and we want that certain amount to reach $2 billion. So whatever they put aside will be invested at 3% interest. whatever they put aside today would have 30 years to accrue interest at 3%. In the last year of the reactor's operation, of course, it would only have 1 year. Whatever payment they make in that year would only have 1 year to accrue interest. So how do we figure out how much they need to be contributing each year for 30 years? So there are several ways to go about solving this. If you've taken engineering economics, you know that there are tables which give different factors, and one factor will be A over F. And so that factor, you would take the future value and you multiply it by the A over F factor. That's appropriate for I equals 3% and N equals 30, and it would give you the periodic payment. In Excel, we could use the payment function, and note carefully how this works. Again, the first number that you put in is the interest rate, 3%. The second number that you put in is the 30 is the number of periods, in this case 30 years. And then note that I've got just these 2 commas here, so there's nothing in right there, which would be the case where ordinarily you would put the present value. Instead, I've put in the future value of $2 billion. So this will return $42 million. It will actually return negative $42 million, again, because of that sign convention. But that tells us that we need our ratepayers to be putting $42 million in every year so that we have $2 billion accumulated at the end of 30 years. Let's say here's a third way of doing this. Let's say that you only have the P over F and the A over P factors. In other words, you have a factor, and I gave you formulas for both of these factors. So you have a way to take the future value and convert it to present value, and then a way to convert the present value to an annuity. So here I'm showing the formula that I gave you, and again, you can look up factors if you're used to doing that. Otherwise, you can just use this formula. And I've left out the N in this formula, so I'm going to draw that in now. So the present value is equal to the future value over 1 plus I to the N. The future value is $2 billion. 1 plus I is 1.03, and N is 30. So we get $824 million. So if we had $824 million right now, we can invest that at 3% with the interest compounded and have $2 billion in 30 years. However, we don't want to get that all at once. We want to get it through an equivalent annuity. So let's find the annuity that's equivalent to that present value. And so here we use the present value of an annuity formula, and I've plugged in the present value that we just got from the other formula of $824 million. I've plugged in the interest rate I of 0.03 and the N of 30 compounding periods, and then I've done the algebra to solve and get $42 million. So this is just to show you the way equivalence works. You don't have to go directly from the annuity to the future value. You can find the present value of that annuity and then take that present value to future value. All of these things are considered equivalent. You can get from one to the other via any other intermediate state. So you can take something first down to present value and then spread it out into an annuity. And that concludes this first section of the lecture. Thanks for your attention.